Hello everyone. This morning we will show you our work on RDPEGFX, what we found and how we found it using snapshot fuzzing. First, let me introduce ourselves and explain you the origin of our work. We are three people from Thallium team, Kola, here present, myself, Jérémy, and one of our colleagues who wish to remain anonymous. They will be represented by this my friend cheese, Tom of Normandy. Thallium is a Thales team expert in reverse, vulnerability research, and red team. And surprise, we are hiring. Work presented today follow Valentino's internship. Valentino's work on finding vulnerabilities in RDP. He was mentored by Tom and me. Valentino used WinFL to fuzz the RDP client. Initially, the idea came from a Black Hat talk that also fuzzed RDP client. He eventually got 4 CV and won $6,000 of bounty. Full story and details are present on our blog thallium.re. Valentino also speaks his work at STIC conference this year. His slide, paper, and a video recording are available on their website. Valentino basically built a fake server fed by the fuzzer and communicating with the client. This approach has several limitations. Some channels could not be fuzzed, he has unknown protocol state, and some malformed messages restart the server. That is not ideal for fuzzing. Luckily for us, after that, Overclock released a new snapshot fuzzer, What the Fuzz. We had 3 weeks off, so we decided to try What the Fuzz on this target and work around some limitations. So today we will explain RDPEGFX is or what the fuzz and snapshot fuzzing work, our vulnerabilities, and what we did to find it. Many details are omitted during this talk, but you can find all the information inside our blog. First of all, RDP. RDP is a Microsoft remote protocol. You can connect to a server, send mouse and keyboard input, and receive a video of the remote screen. Many other information can be transported by RDP like clipboard, smart card, etc. This protocol is documented by Microsoft. RDPEGFX is an asynchronous protocol inside a virtual channel that is part of RDP protocol. Go check out our blog to understand RDP and virtual channels. This protocol has about 20 different commands, and commands of PDU for Protocol Data Unit can be grouped together. These commands are used to create surfaces and fill them with data. Every PDU starts with a header that specifies the command ID and the payload length. After that, each command has its own specific content. You now know what RDPEGFX is. Let's talk rapidly about What the Fuzz. This tool is open source and based on the concept of snapshot fuzzing. First, you take a snapshot of the state of your target, memory and CPU. Then you write a harness to insert your fuzzing data inside the target, and you run it. At the end, you can restore the state and retry. This is useful for fuzzing a state machine or a small part of a program. The snapshot is taken using kernel debug. Note that after that, the snapshot, you no longer have access to the disk or I/O. The harness is based on actions on breakpoint and patching the memory or registers to inject data. The fuzzing part is based on different backends, emulation or virtual machine. What the Fuzz has 3 backends. Box CPU for full emulation and a better control. It is slow but powerful. This backend is perfect for setup and debug the fuzzing campaigns. You can also use it for crash analysis or generate full tenant traces. What the Fuzz also proposes KeyVM or Hyper-V backend to have a fast fuzzer based on virtualizations. Coverage is based on one-time breakpoint for performance reasons. Breakpoint is an important mechanism when you use What the Fuzz. For setting a breakpoint, you need to translate virtual addresses to physical addresses. The dump only contains physical addresses, and generally you want to set up breakpoint on virtual addresses. There is a classical path from CR3 to PTE for doing the translation, and here you can have two cases. The easy case when PTE is valid, this case was implemented inside WTF, and the more complicated case when PTE is not valid. When PTE is not valid, you have many reasons for that, and that doesn't mean the translation is impossible. This cases was not implemented in WTF. You can find the details on our blog. So we implemented it to be able to set breakpoints in this case, and we made a pull request. Otherwise, you can also read the doc to avoid this case using lockmem, but we'll read the doc. Kola will now introduce our fuzzing campaigns.
Thank you, Jérémy. So now that you know about RDP and what's the fuzz, I'll talk about our fuzzing campaign, some improvements we made, and the crash we found. As we do not have an exploit, the talk will be more about the journeys and the destination. The first step is to precisely identify the code we want to fuzz. JFX messages are processed in the decode function of the JFX protocol client decoder. And we are interested in fuzzing the white part here, where we can see a dispatcher where each PDU is forwarded to the corresponding handler. In the next slide, I will show the same control flow graph, but with not grouped together, and I'll explain the color code. So again, it's a control flow graph of the same functions. So in blue, we have the function preamble and some preprocessing of the input buffer. And as Jérémy said, there may be several PDUs in a message. So each PDU is processed in the loop, first with some preprocessing, a switch on the command ID you saw in the header. If it's invalid, the PDU is skipped thanks to the PDU length, again declared in the header. And if it's valid, the PDU is forwarded to the corresponding handler. There are some checks, and the next one is then processed. And the red node regroup every exit condition of the loop. So we placed a hook just here at the end of the blue part, just before the loop. We use it to capture corpus during a live session, to create our snapshots and inject our fuzzing data. For first fuzzing campaign, we felt that the hardest part was actually generating a satisfying dump. So if you try snapshot fuzzing for the first time, do not give up if it doesn't work at first, and try harder to get a nice dump. And also, please make sure to activate correctly crash detection if you don't want to feel dumb for a while, like we did. And so the behavior we got with one manager and 7 KVM buffer is this kind of curves, with here the number of basic blocks covered with respect to time over a 24-hour period. In the upper right corner, you have the the size of the corpus, and here, in the lower right corner, the number of executions per second. So actually, this is not the curve of our first campaign. This is, or even our first working campaign. This curve corresponds to a campaign we did last month in order to evaluate some of the improvements we made to our harness and what's the first, because really we tried several things and we don't know what was relevant or not. In order to get a fair evaluation, we ran each of our campaigns 15 times and under the same conditions. And from those 15 curves, we built a curve of medians and a tube around this curve containing 60% of the values around the median. And we did that in order to get rid of outliers, like extremely lucky or unlucky campaigns. So as I said, we did several things. I won't talk about everything. The main thing was to improve the hardness, which is an obvious thing to do when fuzzing, and to play with the coverage. And so there's, again, some advertisement for our blog. So the first step is tweaking the harness. The first naive harness, unsurprisingly, would generate some, actually maybe a lot, of invalid PDUs. So we'll go in this orange part, or even worse, we may fail this test, which is a test where the consumed length, as reported by the handler here, is compared to the declared length in the header. And if the value are not equal, the rest of the message is not processed. So the classical way to handle this is to either discard invalid messages or fix them a priori. So we could not fix them in the blue part at the injection point of the data because we don't have a PDU parser and we don't know what the consumed length will be. So instead, we put a hook at the start of the loop and fixed any invalid command ID with in a deterministic way. So we never go to the orange part. And also we provide a valid PDU length in order to bypass this check in the handler, and we just knocked this check here. And so sometimes the structure of the target allows to do these kind of things, because it never look back and use those values in a different way. So this is a curve we got. So there is a slight improvement in a number of basic blocks covered with one manager again and 7 KVM backends. And the interesting part is that the time to reach the number of basic blocks covered by the blue curve in 24 hours here is like in less than 4 hours. So there is a real improvement in speed. And the size of the corpus is similar in a number of samples, but if we look at the size in terms of kilobytes, it's actually bigger. And it's also expected because the blue campaign with the naive harness will not select big messages containing many PDUs because there is a chance, non-negligible chance that one of the PDUs is invalid. And for the same reason, the speed is smaller because we perform more work for each message. So now we tried also to improve our campaign by changing the way WTF collects coverage. So WTF use basic block coverage, and the industry standard is edge coverage. With Box CPU, it's pretty simple because there are a lot of callbacks you can register. And for example, there's this one, which is called every time a conditional near branch is taken. So we just register this kind of code. When we have non-conditional near branch, we record a value built from the source RIP and the destination RIP. And we do that for conditional near branch not taken also, and some of the unconditional near branches. So this is implemented in pull requests and WTF. And we wanted to go further and implement context-sensitive coverage in order to have the exploration of the code independent for each PDU, because even if they have different handlers, they might reach the same part of the code, and then we want coverage to be recorded independently. So for that, we just added a public attribute to the backend. We set this attribute at the start of our loop in the same hook as before to the current command ID. And when recording coverage, we just combined the edge coverage with this context in order to get context-sensitive edge coverage. And so this is really easy to do with Box CPU, and this is okay. We enjoyed working with that. So this is the curve we got, which is quite unsatisfying because the orange curve also use the improved harness, so we would have hoped to get some improvements with respect to the green one. But the setup is a bit weird because box CPU is so small that we combined 5 box CPU context-sensitive edge coverage with 2 KVM backends with basic block coverage. So actually, almost all of the executions are done by the KVM backends without context-sensitive edge coverage. Still, we can see the effects of this context-sensitive edge coverage when we look at the size of the corpus, which grows much faster. And if we look at the number of basic blocks coverage with respect to the number of execution instead of time, we might see some improvement. So it might motivate us to implement edge coverage in a faster backend. So we did not do it because basic block coverage is done with temporary breakpoints, and we will need permanent breakpoint, which would impact the performances of the KVM backend. So instead, we thought about what other behavioral information we can use. And we already have the set of dirty pages for free because the further needs those in order to restore the snapshot. So we just throw the set of dirty JPEGs into the coverage. And as a side effect, this will favor big allocation. As you can see, again, the results are not very satisfying. We still decided to show you this result because positive results are as important as negative ones. And again, we can see that the speed of execution is getting slower very fast because it's very easy with GFX messages to add a PDU that has a lot of allocation and a lot of writes in those pages. So maybe one improvement would be to only record writes on memory that was already allocated at the start. But evaluating further with respect to basic block coverage is not really always relevant. What we're interested in is the number of crashes found. So this graph is not really exactly that metric. It's the number of campaigns that reported crashes. So what this means here is that, remember, we ran each configuration 15 times, and after 24 hours, only one of the campaign with a naive harness reported crashes out of the 15. And so the nice thing here is that we can see that even though the orange campaigns with the 2 KVM and 5 box CPU backends did not cover more basic blocks, it adds more chances to discover crashes. So this graph should be taken with a pinch of salt, and there are more explanations in the blog. So what kind of crashes did we encounter? So dozens of crashes. So at first, most of them were spurious. They were either linked to an erroneous dump or aggressively optimized harness or WTF modification. So everything was fixed before we did those experiments. So on the previous graph, it's not those crashes, it's the next one. And it was a seemingly spurious crash, which was harder to analyze. It's reported as an access violation right, which is promising, at an address. So we look at that address in the dump, and there's nothing in the dump. So we can see 2 explanations. Either we made yet another mistake, or it's code that was generated during execution. We tried to reproduce it. It reproduced consistently in our fuzzer with a box CPU or KVM backends. But when we tried to reproduce on the real system, it didn't work. And in order to analyze it, we tried to generate a trace, but the trace was huge. I mean, I think it was like 60 gigabytes just for the RRPs. So we could not symbolize it. We could not load it in an editor. We tried some grep magic to reduce it, but it didn't work. So at long last, we decided to look at the specification, and our crash witness was relatively small, just 2 create surface, 1 solid fill, and 1 surface to cache. We minimized it just by removing the PDUs one by one and looking if the crash was still there. So it's just a create surface followed by a solid fill. And looking at the parameter, this is actually what is happening. We are creating a surface and filling a rectangle on that surface that overflows out of the surface. So this is consistent with an access violation right. And so here we were pretty confident that we had a real bug. In order to be able to analyze it, we did some crash trace minimization. It would have been pretty cool if we implemented a fuzzing strategy optimizing for short execution time, but actually we just did a handmade dichotomic search. And we ended with 2 samples, almost identical. One crashing, generating a trace with a reasonable size, and one not crashing. The only difference here in the bottom coordinate, which is slightly bigger as 7F02 in the crashing case, and smaller 7F01 in the non-crashing case. We were finally able to load the symbolized trace in VS Code, and looking for the last relevant symbol, we found JIT copy context in this 3D10 warp. So now we know why the code was not present in the dump, because it's JIT code. And the next question is, what is this 3D10 warp? It's actually Windows software rasterizer, and it's used when no 3D hardware acceleration is available. And we use that information to reproduce it on a real system by just deinstalling our our driver and replacing it with a generic VGA1. The next step is to identify the root cause of this crash. For that, we use differential trace analysis, which is just a fancy way of saying we compared the crash and no crash traces. And for that, we just used the scroll wheel. We loaded both traces in VS Code. It did not complain about loading, but did not activate all the fancy red, green diff colors. But thanks to our scroll wheel, we could identify the last common address here in that function to these 2 traces. So there is a slight offset, but it's the same. And in the crashing case, it will stay in the same function. And in the non-crashing one, it will go to a record error function. So we will use this address. And we generated 10 traces with What's the Fuzz. So to recap, Tenet is a trace explorer by the author of Lighthouse. The last common symbol is this jump here. And this jump is influenced by this comparison between EDX and ECX. In the crashing case, ECX is, I don't really know what side to turn, is very small, and in the non-crashing one, it's very big. And ECX is computing with a multiplication. And I already can guess, if you did not guess earlier, that's just an integral overflow on the check between the bottom coordinate, the end of the right and the end of the surface. To recap, we did some, we had an unvalidated crash, which we could not reproduce in code that was not in the dump, and generating a huge trace. After reading the specification, it seemed legitimate. We did some crash trace minimization in order to be able to analyze it. And we understood that the crash was in JIT code, and that the out-of-bound write was in a D3D10 warp and not in RDP code. We did some root cause identification with diff and some root code analysis with tenant in order to find an integral overflow in context copy immediate data. So what is the impact of this bug? So we have a happy RDP client connecting to a server. The server sends create surface PDU. The client allocates the corresponding memory. Then the server sends a solid fill PDU, and the client will write as the value of the color in the rectangle, line by line, eventually overflowing out of the surface. So as I said, we don't have an exploit, but we have a proof of vulnerability, which is a malicious FreeRDP server built from a Docker file and a FreeRDP patch. We did not exploit it because there are several constraints. I will not enter into the detail. And again, it's not an exploit, it's just a crash of the client. We sent this malicious server to MSRC mid-March together with an analysis of the bug and a few tenant traces. The bug was fixed 4 months later. Meanwhile, the bug was confirmed mid-April. They validated our HEXACON abstract, and we inquired about bounty and were awarded one a week later. So the takeaway here is that even if what you find is a constrained remote write with no exploit in a convoluted attack scenario, here we have an RDP client without hardware acceleration but sufficient memory connecting to an RDP server, you can get a nice bounty if you ask me. So we wanted to share our success with the author of What the Fuzz. We thought about sponsoring the project, but the sponsoring feature is not activated on his GitHub account. Moreover, we've been told and we've been warned that anything even remotely looking like an attempted bribery of a program committee member will not be tolerated. So instead, we went for a thank you card with a few stickers. So I don't know where Axel Souchet here. Can you stand up? And Jérémy, can you give him his envelope? And please join me for a round of applause to Axel Souchet for his tool. So the author of Tenet probably deserves one too, Marcus Gaslen, but he's not here, so maybe he'll come next year in order to get one. So for those curious about the card, it's just 4 trees representing 4 fuzzing strategies. As a conclusion, so we had some fun playing with What the Fuzz and Tenet. We did some on-the-fly modification of fuzzing data because our target allowed it. We experimented with exotic coverages, with some trace minimization, and with all the modifications we tried, it's very hard to know which one was determinant, but we tried at least to do some experiments. And for that, we used What the Fuzz, as I said, diff and Tenet, and IDEA too, so not just free tools. And we also used the nice Microsoft open specification. And before ending the talk, I want to emphasize again that the bug is not in RDP or even in the use of D2ID warp by RDP. It's in, the bug really is in this library. And without hardware acceleration, it's loaded by almost every processes. We didn't try to find another attack scenario, but there's probably one. It's also loaded by some processes when hardware acceleration is loaded. So it might be an interesting target for a further campaign. So anyway, for this crash, it was fixed last July. And anyway, we did not have an exploit. So thank you for your attention. And if you have any questions,